Okay, now we proceed with combustion. So this is actually a combustion of coal. Okay. The chemical composition of coal, we have a carbon. Okay, and then we have H2, O2, N2, and sulfur plus ash. Alright, so this one is non-combustible. So basically, you don't need to consider this a non-combustible fuel. So the one that you need to consider only this CH2O2 N2 and S. Alright. So you've been given 100 kilogram of coal which has their own respective percentage. Right, so since this one is 84.36%, so would be 84.36 kilogram. Similarly, H2 is 1.89 kilogram, and O2 is 4.4 kilogram, N2 is 0.63 kilogram, and sulfur is 0.89 kilogram. Okay, even if there is no mention about 100 kilogram here, right? Okay, if you have this kind of percentage, you might want to use this one. Okay, why? Because take a look at this one. Here is actually the purpose is to determine the number of moles for each chemical composition. Okay, so since you know the mass is actually equals to number of moles multiplied with the molar mass, right? So from there you can determine the number of mole of carbon is equals to mc divided by the molar mass of carbon. Why we put it in terms of kilogram? Okay, 84.36 kilogram, because this one. Okay, we want to divide it into 12 kilogram, right? 12 kilogram. So from there you can get the value of number of moles for carbon, 7.03 kilomole. So having said that, similar approach is determined for hydrogen, oxygen, nitrogen, and sulfur. So we have all the values, the kilomole, the number of moles value for each of rating on this combustion. Okay, so from there what we do is we do chemical balance. Okay, combustion balance. So from there, 7.03 carbon plus 0.945 hydrogen plus 0.1375 oxygen plus 0.0225 nitrogen and plus 0.0278 sulfur plus the theoretical air. Right? Because here stated it burns with theoretical air. So O2 plus 3.76 and 2. Okay, so the product of this coal is going to be CO2, H2O, sulfur dioxide, and nitrogen. Okay, again, just to remind you on ash, it's actually non-combustible, so no need to consider for combustion balance. Okay, so we balance this equation. Okay, we start with carbon. So from there, this one is x. So x is actually equals to 7.03. And then you have we do for hydrogen. So hydrogen here is both are H2, right? So we put it as H2. So meaning y equals to 0.945. Then we go for S. So for S, 0.0278. Okay. So we have Z equals to 0.0278. That's fine. Z 0.0278. Then we solve for O2. Okay. So for O2 is this one 0.1375. 0.1375. Okay, here you have plus ATH, theoretical air, and this one equals to X plus, okay, Y multiplied with O, not O2, so meaning we need to divide this Y into 2, so 0.5 Y plus Z. So since we've known, we already know this value, X, Y as well as Z, right? So from there, we can have our ATH. So ATH is equals to 7.393. Okay, next we can check. Alright, since you already have all, right, X, Y, Z. Okay, no, we want to find for W, right? We want to find for W. So W, okay, we do from the left hand side. So 0.0225 plus 3.76 ATH, okay, right, and 2, and this one is actually equals to W. So therefore W is equals to 27.82. Okay, so now we have all the values of X, Z, X, Y, Z, W, and the ATH. Okay, so we substitute back all the balance equation. ATH is 7.393. X is 7.03. X, Y is 0.945. H2O. And then Z is 0.0278. SO2. W is 27.82. N2. Okay, that's how the balance equation looks like for cool with theoretical air. Okay, the question here asking about the mole fraction. Okay, the mole fraction this one, right? The mole fractions of the products. Okay, so can put it as a maybe. So what you need to do is you need to determine the total product number of moles. Okay, so n product is actually the summation of all the number of moles of the product. So it's going to be 7.03 plus 0.945 plus 0.02878 plus 27.824. So the value here is 35.82 kilo. Alright, so what is mole fractions? Okay, so mole fraction is just let's say Y of carbon dioxide. Okay, this one should be carbon dioxide, CO2. Okay, so Y is actually a fraction for carbon dioxide. I mean, just put it any way, any symbol also can, but Y is actually a mole fraction. Okay, you can put it something like that. Alright, so mole fraction of carbon dioxide is just 7.03 divided by the total number of moles for product. So here you have 0.1963. Okay, so similarly you can find for the mole fraction of H2O and the sulfur dioxide and then nitrogen. So the value here would be 0.02638. This one is 0.000776 and then the nitrogen would be 0.7767. Okay. Okay. The next question is they ask you to determine the air to fuel ratio. Okay. So meaning the mass of air divided by the mass of fuel. So this one is just nm air divided by nm fuel. Right, so from here, since we assume the fuel would be 100 kilogram, okay, it's not assumed because it is given in the question, right? But if you have something like percentage problem, for example, fuel is given in terms of percentage, you can assume it as a the total would be 100 kilogram of fuel, especially if you want to find the number of moles of each chemical composition, right? And C equals to mc divided by the molar mass of those carbon, because molar mass of carbon is 12 kilogram. Okay, so they use kilogram per kilomole. Okay, so here almost similar to the previous example. So 7.393, which is this value. Okay, you have to multiply with this one with 4.76 kilomole because of air, then multiply with the molar mass 29. So here you have 10.2 kg of dry air per kg fuel. Okay, so basically from this example, what you learn is actually the non-combustible. Okay, what happen when you have a non-combustible fuel inside your, I mean, as a part of your fuel, total fuel. Okay, basically what we do is actually we just ignore it, right? And then the next is the assumption of using, if you have a percentage, then you can assume the total fuel will be 100 kilogram, especially when you want to determine NC, the number of moles for each fuel chemical composition, and perhaps the mole fractions. Okay, how we determine the mole fractions. Okay, I think that's all.